So here we are. So from last time we got as far as this point, which is we're going to talk about elements. And so all elements, all atoms of an element have the same number of protons. So you want gold, you want 97 protons. If you have 96 and you add one, it becomes gold. It's like simple as that. So same number of protons. Number of protons determines what species you're in. So if you have 6 protons, you are carbon. Whether you like it or not, you're carbon. The chances are that you will have 6 electrons because things like to be neutral. And so you'll be a neutral atom. But you might be an ion because you have more or less than 6 electrons. So maybe you want 6, but maybe somebody grabs an electron away from you. You're still carbon. But you're an ion, you're a positive ion of carbon. Or maybe somebody gives you an electron. You're still carbon, but you're a negative ion of carbon. The chances are that you will have 6 neutrons because, well, at that level, you like to have the same number of neutrons as you have protons, and so you'd be carbon 12 because 6 and 6 make 12. But you could have fewer or more neutrons. You're still carbon, but you're a different isotope of carbon. So the number of protons is the species. The number of neutrons is the isotope. And the number of electrons is your ionic standing, your ionic state. If you have the same number of electrons as protons, you're neutral. More electrons, you're negative. Less electrons, you're positive. But you're still carbon. Change the number of neutrons, you're still carbon. You may be more stable or less stable, but you're still carbon. Pure elements exist. Gold, silver, neon. Hydrogen was made in the Big Bang. The lighter elements were made in stars that existed in this part of space before our solar system was created. The heavy elements, and it's iron that's lighter than iron and heavier than iron. The iron were created in massive stars that existed as part of space before our solar system was created and exploded in a supernova. Yes?
Oh, sorry. Up there it says the chances are that you'll have 6 neutrons. Does AB stand for something?
No, it's just me typing. Oh. I was thinking I was going to say about or something like that, but it's just me saying. It should be just of.
Chances 6 neutrons, something BC12?
And B.
Oh, yeah.
And B, yeah, it was and B. Sorry about that. No, it's right. About 88, I say 90 because it's easy to remember, but 88 elements occur naturally. We can make others in the lab by using ion beams. You can make others. They don't last very long. Other heavy elements can be created. 99% of the material on the Earth is made up of only a dozen elements. You know, things like oxygen, silicon, nickel, iron. They just put them in different forms, and you have so much of what we deal with. So chemistry, in a way, well, if you're making the common stuff, is using 12 species. If you want to make the exotic stuff, you can have the other ones. Okay. So, all right, we started being able to divide things up into these elements, and along came a guy called Mendeleev. Mendeleev was a Russian guy, and he started making columns of things. So I have a lot of empathy, not empathy, but I kind of admire this guy a lot because I'm a visual thinker. And so it's interesting. So for a year, I was the program manager, and the program manager does the schedule. Classes in rooms with teachers. And for that year, my wall in my office was covered in pieces of paper which had different solutions on them. Here's the thing for that room, here's the room for that person. And I looked at them all to figure out what was going on. Diagrams. I did it for a year, it drove me crazy. I passed it on to a colleague of mine who's more of an abstract thinker, and I've never seen one piece of paper on the wall at any time solving things, because she just thinks of things in a different way to me. And it's just, the contrast is just frightening. You know, she goes to the computer and she messes with it, and she goes, oh yeah, I can do it on Thursday. Where's your diagram? I don't need it. I just look at the times. The times don't mean anything to me. So Mendeleev I really like because clearly he was a bit, well, I'm a bit like him. He's not a bit like me. And basically, he wanted to put things in columns. So he started saying, well, you know, hydrogen, it behaves a bit like lithium, and it behaves a bit like sodium, and it behaves a bit like potassium. They're very, very, very reactive things. Hydrogen, if you mix it with oxygen, explodes, and lithium, man, you can burn lithium and so on. It just goes on. Like sodium, drop a piece of sodium onto water, and it'll have a big exothermic reaction. So you put all the things that look similar the same. And yeah, he probably didn't have this complete table. It was like, he probably only had like, you know, maybe 8 columns or so, maybe 9 or whatever. But he didn't have all these elements, that's for sure. In fact, and we know that because he predicted the existence of some elements. He might have this guy and that guy, and he could say, no, there's going to be something here. There's going to be an element that's going to be discovered that fits in. And sure enough, over the years, we found things. He saw the overall pattern, because he believed that science is simple, and that if we see the pattern, we can see the simplicity. When we deal with things individually, they seem complex. But when we see the pattern, they seem, we see the thing. So Dmitry Mendeleev was 19th century Russian chemist who first proposed the organization of different elements into a periodic table. He was able to predict the existence of unknown elements because of the gaps in the table. Elements of a specific column of the table have a similar outer electron structure and therefore a similar chemical reactions. So the number of protons, in a way, decides the number of electrons. And the number of electrons fit in shells. And it turns out there's a pattern to this. The first shell can at most have 2. It's like a 2-car garage. You don't have to have your cars in there, but you can have 2 of them. And then the next one is 8. And then you go on, and I think the next one is either 8 or, I don't know, more, 18, something like that. So if you have hydrogen, you can put your electron in here or there, or if you excite it, you can put it out there, etc., etc. But what we find is that if I take something like lithium, it's got 3 electrons. So that one's full most of the time, and that one's full most of the time. And you've got 1 electron that won't fit into the inner shell, so it's by itself on the outer shell. That electron is really wants to combine. It don't want to be by itself. So it makes lithium really reactive. If I go to sodium as 11, so let's have a look. That's 2, 3, 4, 5, 6, 7, 8, 9. That should be 10. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Can you see how this has an electron by itself? So it's also going to be reactive. And so the next one down here is 19, sodium. It's also got an electron, 2 8s, 19. 2 8s and a 2 make 18. 1 more electron makes. So can you see how it's not so much how many electrons you have, but the configuration of the outer electrons. Over here, helium has 2. That's completely full. Neon has 10. No electrons in the outer shell. Argon has 18. No electrons in the outer shell. So this column is really unreactive. Doesn't even want to form a molecule with itself. This over here, this column, incredibly reactive. And so the pattern of the behavior depends upon the structure, the design of the electron shell. And do you have an electron by itself, or 2 electrons by themselves, or 4 electrons by themselves? So, for instance, carbon, 4 electrons by itself. Silicon, 4 electrons by itself. Germanium, 4 electrons by itself. And so we find similar behaviors for similar types of configuration. So that's very useful from an interpretation point of view. What's not so obvious, if I take, say, hydrogen, which is a proton with one electron, and I take, say, well, let's just do carbon, actually, which is 6 protons and 6 neutrons and 6 electrons. I don't know about you, but I'm cramming in 14 more things. So I expect it to be a lot bigger. And it turns out it's not actually like that. This is like drawn a bit to scale. And yeah, hydrogen's quite small, but if you look at these guys down here, these are not much bigger than those, although there's a lot more stuff in them, and so on. And so we get this thing where we say a typical hydrogen atom consists of 1 proton, no neutrons, and 1 electron. A typical lead atom consists of 82 protons, 125 neutrons, and 82 electrons. Yet their sizes are not so different. Hydrogen has a radius of 0.052 nanometers, and lead has a radius of 0.14. It's 3 times bigger. So lead is 3 times bigger than hydrogen, and yet it's got, how many more protons? What happens is the more protons you have, the stronger the electric field. And so it pulls the electrons in. It's like a more massive planet pulls the moons in. And so there's not that much change in the spacing or the size of the atoms. Now, what is the size of the atom? Does this thing have a shell on the outside? No, it's an electrostatic thing. So there's a positive electrostatic field, and then there's an electron cloud around it. And we visualize it in different ways at different times, but it's kind of like you look at the material and you kind of say, what's the interatomic spacing? That's relatively easy to work out. And you kind of divide it by 2 and then say, there's your size of your atom, Because it's not like a shell. It's like it's like a pillow. What's the size of your pillow? I have no idea what the size of my pillow. Roughly speaking, I can tell you, but I can't measure it with precision. So isotopes. Isotopes they're not important at all for chemistry. Chemistry is all about electrons. Isotopes, all about, very important for nuclear physics. So you want to know about radioactivity, you want to know about fusion, you want to know about fission, atomic bombs, nuclear power plants, atomic medicine, nuclear medicine, which is really important. It's interesting, actually, just among the community of teachers, some people don't go near nuclear. They just feel very uncomfortable with it because it's all about bombs and, just kind of depressing stuff. But if it wasn't for nuclear medicine, people would die a lot sooner in many cases, because a lot of illnesses are treated with nuclear medicine. And you can have one without the other. I'd like to go through my entire life without having a nuclear bomb going off. But you can't have one knowledge without the other, let's say. And, if we didn't have knives and forks, we'd have nobody stabbing anybody, but we'd have eating with our hands all the time, which I don't know. It's all right, But so it's the yin and the yang of. There's this thing about for every so my daughter is stubborn, which means she's tenacious. It's just stubborn when I don't like it, and tenacious when I do. It's a value statement, isn't it? It's my judgment of her behavior, whether I use the word stubborn or tenacious, and I praise her for tenacity. And I punish her for stubbornness, which is really praising her for how I feel about this. It's like, when I like what you do, I'm going to give you candy. When I don't like what you do, I'm going to tell you off. And it's like, it's the same trait. So, as a physicist, I'm glad we have nuclear. I don't want it in bombs. I don't want it in power plants particularly. I get concerned about power plants. But, I do want it in the hospitals, So it's interesting. So It's all about the number of protons, number of neutrons. As you put more and more protons together, they don't want to be together. It's like putting more and more springs inside a tin. And they're going to want to get out. And it makes them more and more unstable. It's helpful if you can dilute them. Just keep them a little bit farther apart. So we tend to have neutrons which basically spread these protons out. And if you plot a graph of the number of protons versus the number of neutrons, for the beginning bit it goes like that. 2 protons, 2 neutrons, 4 protons, 4 neutrons, 8 protons, 8 neutrons. But what happens is as you go to higher masses, you tend to need more neutrons. You need to be able to dilute the protons, so you put more and more neutrons in. And when you don't, you get unstable nuclei. And so, for instance, uranium, there's various isotopes of uranium, and some of them are more stable than others. So for a nuclear physicist, they're not interested in the number of electrons, they're interested in the number of neutrons they have for a given species. So we say the number of protons defines the atomic species, the chemistry of an atom depends upon the atomic species, because that determines the number of electrons. Gold is gold because it has 79 protons. If I take something with 78 protons and I add a proton, it will look like gold. So you can turn, if I mess with lead enough, I will turn it into gold. The problem is, it will be so expensive to do that, I'd be better off just mining for gold. It's like it's not worth it energetically. But in principle, it can happen. Interesting little anecdote. Newton. Newton, we do Newton all the time. Spent 10 years of his life doing physics. And in that 10 years, he did basically mechanics, optics, and we teach him all the time. The guy was amazing. Spent 10 years of his life doing alchemy, trying to turn lead into gold, and got nowhere with it because they didn't have the science of the nucleus. They just knew mixing things together, and so it couldn't get the energy needed. So in principle he was right, but he spent 10 years mixing up these brews of things in his little room. I'm surprised he lived through it, but he did. He spent 10 years trying to commune with spirits. That was his third thing. And, no science output. And then he became like a bit of a politician. He became the leader of the Physical Society, and he became the master of the mint in London. Became quite a powerful person, actually. But 10 years spent trying to do alchemy, and they did not have the technology to do it. It's not that it, in principle, can't be done, but you need to mess with the nucleus, and that is a very energetic thing. The number of neutrons determines the isotope of the species. A given species can have a number of isotopes, so gold can come in different types of gold. They behave chemically the same. You cannot tell the difference. It's very hard to get gold which is only one isotope versus gold which is another isotope. There's naturally occurring mixtures. Gold has one stable isotope, that's Au-197. That means the number of protons plus the number of neutrons equals 197. This has 79 protons and 118 neutrons. Gold also has 18 unstable isotopes. They don't survive as long. They change into other things. Au-195 is the most stable of these so-called radioisotopes. Of the ones that are unstable, this is the most stable. It has 97 protons and 116 neutrons. Au-195 has an average half-life, average lifetime of 186 days before it transmutes into another species. So after 186 days, it goes into being something else. Bit less gold. When it's as short as that, and this is the most stable, this is like the longest lasting one. Pretty much when you formed the gold, it went within, a couple of years, it was gone. We can rediscover it through various various nuclear means. We can recreate it and say, how long does it last? We can take nice stable gold and hit it with a nucleus and see what happens. But by and large, those species which have a short half-life don't live long. They change into something else. So we tend to see the things that are more stable. Now, that's not to say it transmutes once and then it ends. Sometimes there's these cascading families where it starts off as one species, one isotope, and it changes to another, and it changes to another, and it changes to another. And if we go back a bit, this is not. So one of the classic things is uranium. Where's my uranium gone? My uranium is there. There's my uranium. And one of the things I can do is I can emit an alpha particle, which is a helium nucleus. And so I lose 2 positive charges, so it goes to thorium. And then it goes down to 88. And where is 88 on here? It's somewhere on here. 88 goes down from there to radon, and then it goes to 86 probably. So it would go to over here to Rn, and then goes to lead. So just by doing those, click, click, it goes through. So you might see some radon because it's took a while to get there, Okay, so then the next bit is, let's talk about combining things. If I take sodium and I take chlorine, first of all, chlorine kills you, sodium burns you, you put them together and you pour it over your food because it's salt. So hold on. Compounds of arsenic kill you. Completely different chemistry depending on its state. Aluminum oxide, very unstable. Aluminum, very stable. It just goes on like that. So when we combine things, they will either combine chemically or they won't. They're the 2 extremes. So if I put a whole bunch of hydrogen with a whole bunch of oxygen, I'll tend to form water. Now, if I have too much oxygen, I'll form H2O with some O2 left over. If I have too much hydrogen, I'll form H2O with some H2 left over. I won't have hydrogenated water. It won't be like that. It will be, that's what Dalton saw. Very specific ratios for these things. So if I get the right ratio, I'll have all of it goes to water. If I take nitrogen with hydrogen, I'll form ammonia. If I form carbon with hydrogen, I'll form methane. If I take sodium with chlorine, I'll form sodium chloride. They're all compounds. The properties of the compound are distinct, very distinct from the properties of the constituent species. You can't look at the elements and say, I think it's going to be like this. Completely different. If I take things that are kind of stable, they're usually compounds, and I mix them, I don't get something new. I get a mixture. So I get milk is a classic example of a mixture. It's kind of like stuff inside stuff, and they don't want to combine together. They just occupy the same space. They've got a certain proportion. They basically, if you took out a cup of milk, it would be like a cup of milk, would be like a cup of milk, But there's no bonding between them. So air is nitrogen, oxygen, carbon dioxide. There's a little bit of carbon monoxide. There's some CH4 in there, some methane. There may well be some ammonia. There's some neon and so on. But they're never going to combine and form this big, you know, NOCO2NeH4 compound. That's never going to happen. It's just going to stay as these distinct things. So they coexist. They don't combine. And you can kind of see, you kind of like it's like hydrogen atom wants to combine, and oxygen wants to combine. So so hydrogen has one little electron, and hydrogen has one little electron, and the oxygen, if we look back at our periodic table, oxygen has a number of 8. So if we think back, that would be 2 on the inside and 6 on the outside. So we have 1, 2, 3, 4, 5, 6. There's 2 openings. Oh, I can take that slot. Oh, I can take that slot. So there's a reason why it's H2O. It's not going to be just H7O because there's not that slot. So there's a clear type of bonding taking place. So when you get unsatisfied bonds, when you get empty electron spaces, or you get electrons that are not happily in a shell, you get combination, you get compounds. When you have a nice glob of some gelatinous fat in your milk, it's happy, it's bonded. There is bonding inside it. It's bonded. It doesn't need you. It's just going to coexist, but it's going to ignore you. You know, that's a mixture. So molecules. Molecules consist of 2 or more atoms that bond together by sharing electrons. Oxygen gas is made of molecules because oxygen atoms pair up to form O2. Argon gas is made of a single atom because they don't combine with each other. There's 8 electrons in the outer shell, so it's content. Oxygen is a molecule that consists of 2 hydrogens and 1 oxygen. Energy is associated with the bonds between the atoms of a molecule. So sunlight pays for photosynthesis, which creates carbohydrates that we convert into energy when we eat them. So it's a very interesting dance. The sunlight gives us energy, and that stimulates bonding. There's energy in that bond. We then take that food into our stomach, and we maybe just simply split it up, or maybe we combine it with different things, but we get some of this energy. Not all of it, but some of this energy, and that pays for our actions, our bodily functions, our running, our climbing, paid for by the sunlight. So we are, to a great extent, a solar device. No sun, no plants, no vegetables, no food, no us. You know? And no sun, no trees, no coal. No coal, no coal. No sun, no trees, no oil. So you can look back at most of your energies and say, how many of them come directly from sunlight? And most of them do. Geothermal energy does not. Geothermal energy is from the formation of the solar system, including our sun. So geothermal energy is kind of fundamental type of energy. But all the others, wind energy, solar energy, heats up gas, hot air rises, forms an imbalanced current flow. It's paid for by solar energy. So solar energy is like the fundamental starting point for most of our energies. Let's get weird. Matter and antimatter. So they found the electron, and they found the proton, and they found the neutron, and they do experiments where they'd fire these particles in, and they'd get these, different things going off, And these are using cloud chambers. And the nice thing about that is you can see by how long the trace is, you see how fast the thing is going. If it's going really fast, it has a longer trace. If it is not so fast, it has a shorter trace. And we can see is it charged or not. So you can look at the angles and you can do mechanics. You can do a collision. Just general physics collisions. And you can figure out what's going on. And what you find is that there's a whole bunch of energy missing. And if you do mechanics, you find out that the little particle carries away most of the energy. It's just one of these sad things. If I have a semi and I have a little car, it's the little car that zooms off with an incredible velocity. And because it's a half mv squared, it steals most of the energy after the collision. The big particle, the truck doesn't change its speed by much. The little changes speed by a lot. So it's unfair. But the energy is carried away by the little particle. And it's the energy that causes damage. And, you know, that's why it's safer to be in a big vehicle than in a small vehicle. That's just the way it is. And that's why, for instance, my brother drives a big car. He says, I feel safer in it. And he's right. It's like I drove an Odyssey. When my daughter was born, we bought an Odyssey. I loved that car. It was like you could see, and people would kind of like keep out of your way a little bit. And then we went to Honda Civics, and people just ignore me. It's like I got to watch out. And if I'm in a crash, there'll be much more effect on my car than on a big car. You know, so just the way it is. So Enrico Fermi says, we got missing energy. Oh, it's going to be a little particle, because the little particle takes the energy away from mechanics 1. And it's going to be neutral, because charged particles are easy to find. So he calls it, because he speaks Italian. Anybody speak Italian? He speaks Italian, he called it neutrino. Little neutral one. That's what he called it. So we have the electron neutrino. So, okay, we got 4 of these things now. We start trying to work out more particles, and at one point we had 200 particles, and then we realized not all of those last very long, and we got it down to, I think it's 16. There's 16 particles as a grid with 4 by 4 basically. And these on this column, they're your mediating particles, so that's your gluon and your graviton and your all that kind of stuff. And for every particle, there's an antiparticle. So the neutrino, the electron neutrino, is the kind of antiparticle for the electron. I'm sorry, that's not true at all. So every now and then they would see a thing and they'd get a particle going in what seemed like the wrong direction. They'd get that rather than that. And they go, ooh, what's going on? This is an electron, so what is this? And they call it the positron. And they said that's the anti of that. So for every particle, there's an antiparticle, both in terms of the species, and also we believe in terms of the number. Literally, for this positive particle, for this particle, there's an antiparticle. When we look around our local environment, we don't see many antiparticles. And so which raises the issue of when we look at Andromeda, is that a galaxy made up of particles or antiparticles? It could be either. We tend to think that there's more particles in our part of the universe, but, you know, who knows? So every particle has an antiparticle. The electron is paired with the positron. Proton is paired with the there's a simple one, antiproton, yeah? Let's keep it simple. Oh, anti-Bonaquisti, there's an anti-Bonaquisti out there. 1995, an anti-atom was made by getting a positron to orbit an antiproton. And they made it, and it was this atom that was made of antiparticles, but it behaved just like an atom. Didn't last for very long, because when you get a antiparticle meets a particle, they go back to energy. The idea is we had energy and we made particles and antiparticles. For some reason, we're pretty much made of particles. If we recombine them, they go back to energy. So gravity acts in the same way on matter as antimatter, but it's not obvious if distant galaxy is made of matter or antimatter, because it's just going to behave the same way. But if matter meets antimatter, the two will annihilate each other with the production of much energy. We believe that the visible universe is primarily matter. I think partly because we don't see a whole bunch of annihilation, even though we do see galaxies hit each other. We are colliding, by the way, with Andromeda. We're going to eventually collide, and we'll be subsumed by them. Matter and dark matter. So now, okay, we had matter and antimatter, and then here's an interesting thing happens. So we did circular motion. So we found that if you had a rigid disk, then that travels like that. Remember that? Yeah? And so if you're on the outside, you travel faster than if you're on the inside. So people started looking at galaxies. And galaxies are not rigid disks. But what they saw was there was like constant speeds on the outside. And then there was this fall off. But there was this constant speed on the outside. Well, that's not because it's not a rigid disk. Under that argument, you can have anything you like. It's like, you can go around, you can drive your car in a circle any way you choose. You can have any direction, we can have whatever you want. So it's not that every planet or sun in that galaxy over there is doing what it likes. They're obeying physics. And so if this is what we expect, and this is what we get, how does gravity compare with this? We have the center of the galaxy, etc. We can do math modeling. And if we take into account all the visible stars, for example, in Andromeda, and we do gravity on them like Newton would, we don't get this behavior. So people then started to say, well, what would we need to get this behavior? And they discovered that they'd need mass that was not obvious to us. We couldn't see it, so they call it dark matter. And it extended beyond our galaxy. Okay, so there's dark matter, it's beyond our galaxy. There's a theory. Other people were saying, no, it's just that gravitational field strength, the little big G changes with position, so we can explain the same thing. So, two theories. Then people started looking at pictures of distant stars. And what they noticed was, they'd be like, it'll all look pretty normal. Then there'd be this star or this galaxy in the middle. And there'd be these like wispy things around the outside like that. And on a few occasions, because of the temperature, they were clearly a different color. And so people started saying, what's that smear? It looks like a smeared out galaxy. And it actually looks like a really distorted lens. And then they started realizing, oh, I know what's going on. There's this galaxy back here. And as the light comes by, it should miss us because my eyeball is there. I should not even see it. But because of the bending of light, I get to see it. So it's like a distorted image. Well, okay, let's do some calculations on that distorted image. So they do some calculations, and what they find is, I know how much mass is here, and Einstein did this with the sun, so I should be able to work out the bending of light, bending of space-time, and it's wrong. And there's missing mass. Oh! There must be a whole bunch of dark matter here that I'm not taking into account. So 2 different ways of justifying dark matter. First of all, looking at the rotation rate of a galaxy that's relatively nearby. And secondly, looking at these so-called gravitational lensing effects of galaxies that are far away. They both point us in the same direction, and they're actually quite consistent with each other. So when I first heard about this, I said, this is nonsense. But the second different way of seeing the same answer, you've got to take it seriously. And this is an actual photograph of an image, computer image, but it's actually made from pictures where they've actually got, you can see the bright bits of the galaxies, and they believe that this is dark matter actually around these structures of galaxies. So that they believe they can plot it out. Yeah, it's a model, it's a way. So we say, here's the shocker. If we want the universe to work according to Newton's laws of gravitation, we need to have more mass than we can see. Here's the shocker. Some percent that 90% of the matter in the universe is dark matter. So everything, 9/10 of what is there, we can only see the gravitational effect of. We can't find it, we can't point to it, we can't say, here's a bucket full of it. 9/10 of it, we can't find. I just find that scary, isn't it? I mean, 9/10 of the universe is we've got no idea about. You know? It's like, what is it? I have no idea. So can you understand how these particle physicists get really excited about this kind of stuff? Because they're working on the fundamental stuff of the universe. And they're getting answers that on the face of it seem bizarre. And yet the science says they're true. Or at least logical, the next step. We might change our mind, but that's where it's pointing. It's kind of exciting. It will not make, doing this will not make penicillin work better. It will not make a better semiconductor, won't make a computer go faster, will not save any lives. Won't do a thing. In some ways, it's complete luxury. But in another way, you could argue and say, well, if we're not going to look at these questions, why are we here? Is the purpose of life just to make a better computer? I don't know. Maybe it's... Anyway, so then again, it's never been seen. So there's this big question mark about it. I think that's the end of it. So let's stop that there.